Hey, good morning, everybody. Thanks, Sheldon, for the introduction. So yeah, let's dive right in. So today I would like to talk about some of my recent work. So when we want to create animated characters in games, we usually start out by gathering data. We go to a motion capture studio. We have a mocap actor, we put him in a suit and have him perform some whatever movements we want him to perform. Then some poor animators need to go in and need to find the necessary bits and pieces. They need to make them looping, make them such that they loop, make transitions. All of this we put then later into a giant animation graph. So each of those nodes in these graphs represent a little animation clip. And all the lines connecting the nodes represent transitions between those nodes. And then game code needs to drive this. It needs to set blend parameters and trigger those transitions. And at the end of the day, we get an animated character. That is intentionally a very simple example, but hopefully this whole concept from gathering the data to getting an having an animated character on screen makes sense. So what if we could just create handcrafted animations or capture motion data and use the data as skipping that middle part, and as a result have something like this. So just to emphasize this part, this demo, I only wrote the game logic and used, in that particular example, roughly 40 minutes of motion capture data. And Kinematica decides which pose should be rendered at any given point in time. And Kinematica is the system that I'm currently developing with some of the guys here next door. We announced it last year at Unite Berlin. So just a little bit more about myself. I didn't know that I get such a nice introduction. Well, I released my first game on a C64 in the 90s. Couple of PlayStation 1 games over the course of the 90s. In those games, I did everything from rendering, AI, pathfinding, animation, you name it. Then fast forward a couple of years later, I worked on Hitman Absolution for IO Interactive. Later, I joined Ubisoft and worked there on a couple of projects. So let's talk about animation graphs a little bit more in detail. So usually we have the game logic itself. If you write a game, you need to decide in what state the character needs to be. And that is the logical state. It could be sort of like the character is moving around on a flat surface, uneven terrain, swimming, flying, melee fighting, you name it. But there must be a logical state that dictates what the character is in. And on the other hand, we have then an animation graph that basically replicates this logic. So it or mirrors that logic. And at least if it's a nicely set up graph, if not, you are in a you have a really, really hard time merging those two. Anyway, so game logic decides what state it should be in and triggers transitions such that the animation graph follows the logic. Actually, so here's a little example. That's the third-person character example that Unity ships with. And I thought that actually has a really nice, tiny little bit of code snippet that shows that shows this point. So the animation graph for this character looks like this. He can just walk around. There's top level state. Inside that top level state is a blend tree. Then we have a transition into a crouching state. It also contains a blend tree, and the same goes for jumping. And then this is the code that drives this this graph. It basically gets some inputs from the gamepad. Then in order to determine if the character is grounded or not, we actually cast a ray that starts at the character's hips, and we cast it downwards. If it hits the ground, then we know that he's grounded, otherwise not, and he can jump. And at the end of the day, those set floats and set bools, that is actually the communication that goes towards the animation graph that triggers this logic. And well, why do we do all of this? First of all, animation graphs are really nice because gameplay has extremely tight control over what's going on. We can exactly determine what pose a character is in at any given point in time. It provides a structure for animation clips, and it allows the game code to reason about the animations. On the other hand, well, it's a nightmare to set this up. Every single transition has to be spelled out explicitly. And imagine you already have an animation graph that contains 2,000 nodes, which is nothing. In Assassin's Creed, we had something like 40,000 node animation graphs. And imagine you want to add a new movement state. You have to draw transitions from every possible input state to that. It's very error prone, and things can go horribly wrong. Overall, it's a combinatorial explosion by definition, right? A couple of years ago, I worked on Hitman Absolution, and when we got around to implement the crowds for the game, we only had an animation graph-based system in our game engine, but we wanted to have 1,200 characters being simulated at any given point in time. And well, to no surprise to anybody, this was too slow. So we brainstormed and thought about, hey, what could we do different? And then the AI programmer on the project actually asked me, hey, what if we just make animation clips and you sort of like given the AI goals, which are extremely simple. They are just like go to that position and do something. You figure out which animation clip to play. And I was like, oh, that sounds actually pretty simple. So we ended up with an extremely simple scoring system. All the animation clips were arranged such that at any given pose, you could transition into any other clip and it would make sense. So it was trivial. The game shipped with it, but I sort of like kept thinking about this, hey, if we can do it this way, why can we not just sort of like throw away animation graphs, have arbitrary animations, and can we sort of like still make sense out of it? So the AI or game logic just tells us what it wants to do, and we figure out of this sea of poses, what should we do at any given point in time? So that was the basic idea. Fast forward another couple of years, I had this prototype up and running, and in that prototype the character is strafing, which means he's always facing towards the camera forward direction, and he's moving sideways, forwards and backwards, and that's usually a problem if you work with animation clips. The system handles it pretty well, I would say. We had also the character could run, nice plants and turns and everything, and come shoot. And we had this IK system that was layered on top of it for the character to be able to sort of like raise his arms and shoot. And that resulted in this talk that I gave in 2015 at this totally unknown conference called Nuclear AI. If you Google for my name and motion matching, you will find this talk. And here I sort of like explained all the details that went into this prototype that I just showed. So what's the basic idea? So let's say we start out with some raw motion capture data. Character in this case is performing plants and turns, and we sort of like decide on a little routine that he would perform. So if you pay close attention, he's making 45-degree turns, 90 turns, and so on and so forth in quick succession. And if we now look at the data in engine, I'm moving this time slider here on the right, and the corresponding pose is rendered on the left side, including the root motion that comes directly ahead of this reference pose, subject to some time horizon. So in this case, it's 1 second. So the green line indicates how would the root node move starting at this reference pose. And if you now imagine you have a large number of, let's say this is the current reference pose I'm in, and I have some control signal, we'd simply search across the entire database for a combination of pose and trajectory that matches. I explain that in a little bit more detail in a second, but I just wanted to talk about pose comparison. That was the first idea that I had for how to sort of like find, given the reference pose, which poses would match. And in all the papers that I read, it's sort of like always like, oh, sounds like it's a solved problem. I don't think it's actually a solved problem because it's rather difficult. So I had this extremely simple idea. Well, we just take, so the yellow pose is the reference pose, and the darker yellow pose is the pose that comes right after it. And here, I'm only using neck and feet if the character is just in locomotion. So the delta between the current and the next pose gives us an extremely crude approximation of the velocity at that point. And the blue skeletons are some candidate pose that we want to sort of like measure how well does this other pose compare to my reference pose. And well, that's a very crude way of doing it. It works kinda, but imagine you have, let's say, a joint that points upwards. That's the yellow line in the bottom here. That would be my reference pose, and you have a candidate pose where my joint is sort of like at a right angle. And let's imagine in my reference pose, it moves this way, and in my candidate pose, it moves that way. A blend over time would still look fine. So the crude approximation here on the right gives good results, but it rejects a lot of candidates that would still be valid. And I've seen a lot of papers that people use local joint rotation delta. So basically, they measure the rotational error across local space joints, which I think is totally flawed, because usually we're only interested in the overall pose. We consider to match if the leaf joints are sort of roughly in the same position and move roughly in the same direction. If I have a slide, let's say in one pose my arm is oriented like this, in another pose my arm is oriented like this, there's an error in my shoulder joint, but I don't care about it because in character space or world space, my wrist joint is roughly in the same location. So this also rejects a lot of good candidates. So let's say we have this very crude pose comparison, and we run through the entire database and find an entry where the pose roughly matches and the trajectory that lies directly ahead of this candidate pose matches my control signal. We basically continue from that point. That's the basic idea, and it's extremely simple. Well, if we implement it just like this, you get this kind of result. So the arrows on the bottom here, that's the control signal. And we're basically searching for a new pose every frame, and we switch to that, and you can see the character sort of like stuck in a single pose, and because that particular pose has still a displacement, he's sliding across the floor. So that's, of course, really bad. What's happening? Well, let's say, imagine you have the entire motion library as, imagine that as a single film strip, and we're currently in that middle pose at the top here, and we search for a candidate because that crude geometry comparison would find, let's say, that pose here at the bottom. Next frame, we do the same thing again, and that would then find, that happens, it would find a pose that is 2 frames before the frame that we started 2 frames ago. So basically, you work your way back in time, or you get stuck in the same pose. So to get to this result here, it used exactly this algorithm, but getting to that result required a lot of black magic and fiddle around with the pose comparison to make sure this case doesn't happen with all sorts of special cases. So what I really liked about this approach was that so you can actually see the result if you play For Honor and you walk in a tight circle. you get exactly this problem, where the character gets stuck in a single pose. So the pros of this approach is that it preserves a really high quality result. It does not rely on any faces. I don't care what it is. You can use this for quadrupeds. I made a demo for dogs, and it worked just well. In that prototype here, you could crawl on all fours, and that all worked really well. And it's super easy to implement. In this particular prototype, we basically ran this brute force approach, where we literally exactly compare each and every frame, and we spread using a task system across all cores. It was like insane, but it worked. The problem is, of course, everything that I said so far. The manually tweaking those cost functions is really a pain, and it's unreliable. It requires a lot of tweaking, and it doesn't scale. And we have this back in time problem. Well, when I then thought about I then joined Unity, and I said, well, I really want this to, I still like the idea, and I really want this to be something that everybody could use, but I can't really possibly ask people to manually tweak cost functions. So I looked at all sorts of different motion synthesis research that is out there. I really like Daniel Holden's paper, the phase function neural network. I also really like Deep Loco from Jason Peng. It's a reinforcement learning physics-based system, so it was not really applicable. Then I came across Sebastian Starke's paper. That's the Wolf demo. The paper is called Mode Adaptive Neural Networks. I also really like, again, from Jason Peng, Deep Mimic. It's again physics and reinforcement learning, so I wasn't too interested in the physics part, but I still in depth looked at his project, and it was really interesting. Pretty recently from Facebook research, QuarterNet, that also looked like something where I could sort of draw some ideas from. Overall, all of these projects have sort of like slight little disadvantages that made it sort of like impossible to use in my case. So first and foremost, all of these research projects focus on locomotion and specifically on cyclic animations. And that's just not the case in games. They also use a specific way of advancing animations. They use a concept of phase. I'll show that in a second, and some other disadvantages. So let's look at this in a little bit more in detail. So why are these? Okay, just took a little while. So locomotion and cyclic motion. So any project that focuses on locomotion and cyclic motions is not really applicable to games. Why? Well, let's say on the top right here, I have a wall run, parkour trick. At the bottom here, I have a sword evade movement. I need to be able to use these or produce those kinds of movements. Otherwise, a project is, I can only use it for locomotion and cyclic motions, which is really just not good enough. But the what really struck me as being sort of like a little bit strange is that all of these projects, research projects, except mode adaptive neural networks, use phase as a temporal progression. So what is phase? So basically, it's a scalar variable that is usually in the range from 0 to 2 pi that indicates the point in time of the current pose in a locomotion cycle. So if I'm in that pose, that value is 0. If I'm through the entire cycle, it's 0 again, right? And in the middle, it's pi. And that is actually a code snippet from QuarterNet. That was sort of like the most explicit way I could find where this is right in your face. So basically, here we produce the next pose. And here they have a separate function that basically increments the current phase, which has nothing to do with the actual animation pose. Phase function neural network actually produces this phase increment as part of the actual network inference. And if you're slightly off, you get horrible results, and you're most of the time off. So, and the other thing that is interesting is, if we think about it, there's an implicit assumption. It's basically, we assign a phase value to each and every animation pose. And if we restrict ourselves to locomotion, it says, well, given a specific phase value, I can transition into any pose that has the same phase value, which is just not true. And I have an example for that. So here's a little plant and turn. So the character is turning to the right while moving to the left. And if I show that in slow motion, so here the guy is performing a right plant, left plant, and another left foot contact. So it's a little hop, and he makes contact with his left foot twice. There's no right way to assign phases to this case, if you think about it. So here's another example. It's another plant and turn with a twist. But I can find examples like that if I look at real data everywhere. So right contact, left contact again, right contact, right contact. So double left, double right. Again, it doesn't matter how I slice the cake, I can't assign phases to that. If I assign phases to each individual hop, it would violate the assumption that I can blend two poses that have the same phase, and the same holds true if I assign phases across an entire hop. So there's one commonality across all these projects that I sort of like referenced, and they're all basically autoregressive methods. So given some gamepad input, we produce a control signal. So the point here in the middle, that's the current position and rotation of the character. And the line that leads into that is all the past transforms, so all the transforms our character went through in the last second. And the positions ahead of that point is the actual control signal. That's the desired movement in the future. Then we take the current pose of the character and our control signal, construct a feature vector, pass that through some network, and the network produces the pose that we render this frame. And then next frame, we take that frame as input, and so on and so forth. So it's pretty genius. I really like it, except that it has some problem. I mean, this how we progress time forward is really a big problem, and that is why everybody's using phases. So this is a very old video. This was sort of my first attempt with autoregressive methods, but I didn't use phase increments. This was trained on a single walk clip. It's on the spot, and you can, if you pay close attention, you can see there are slowdowns right here and right here. That's not because Unity drops frames. It's because the network has it's not enough information for the network to produce the right next pose. And in that case, there's not even a control signal. I basically pass in the past two previous poses, so we have the velocity and the current pose, and just try to perform an inference for the next pose. And there's not enough information to naturally progress the animation forward. It's a toy example, but I think it highlights the problem. So, and then Daniel Holden came along with this pretty genius idea. It still uses phases, but the idea is still genius. So he uses an autoregressive network, but the weights are not constant. So basically, we have this phase value, and we have a function that's the actual phase function that produces the weights of the network. So the weights change depending on the phase the character is in. So basically, we have an infinite number of networks that where each network is trained to produce the next pose given the current phase value. So the idea in general, I think, is genius. But here we can, that's exactly Daniel's demo project. But I turned off IK. And that's just the character idling. And there are perfect idles in the data. And we can see that the character is just swimming. And if you pay close attention, he's even growing and shrinking. There's a lot of pulsating going on. And the data, again, there are perfect idles in the data. So here's the same demo just locomotion. Again, IK turned off, and I'm trying to perform a planted turn. I can't. I don't know why. Here the character is moving backwards, even if I'm trying to sort of like tell him to go to the right. And there is a lot of swimming going on. All the data is perfectly fine, and all the foot contacts are really stable. But the network sort of like, because well, I have an explanation for this, but I get to this in a second. Then I came across this research from Facebook, Coordinate, and they had this GIF on their website, and it was like, oh, maybe that's the solution. And then I rendered exactly the same data, just with a fixed camera, and we can see that there's, again, a lot of sliding going on, even though the data is there. So it really tricks you to think that this works, but since the camera is always fixed at the hips, you don't notice this problem. So where does the swimming come from? And my best explanation is, well, let's say we have, during training, two examples, two motions that are nearly identical, but they are not exactly identical. They are just slight variations of each other. Since the neural network does not remember the individual examples, obviously, the only chance it has is to learn an average. And if I learn an average of two movements, my root movement does not match my leg movement, and I don't make precise contacts with the environment anymore, and I get the swimming out of it. And the more data I use, the worse the problem gets. So, and that's actually a quote from one of the papers. Neural network is compact, requiring only a few megabytes of memory, even when trained on gigabytes of motion capture data. Well, that's true. The size is determined by the size of the network, the memory size. But because of the previous argument, we basically throw away all the fidelity that was in the original data. So I'm not sure if that is really a good thing or a bad thing. And as a disadvantage for methods that keep all the data, it was like, oh, this other method requires you to keep all the motion data. Well, again, I'm thinking this is not really a disadvantage. So there is another problem with this kind of autoregressive methods. So especially Sebastian's demo, the demo with the wolf, he had locomotion and jumping. And both were modeled as an individual state. So you had locomotion state and the jumping state. And you still have this control signal. And on top of that, you have this bell-shaped curve for jumping, let's say. It's a scalar value. If that scalar value is 0, we are in locomotion. If we are in 1, we are jumping. And it's the game code's responsibility to ramp up and ramp down this. Well, it's pretty obvious that it highly depends on how fast we ramp it up for how this jump really looks. We lose the actual coiling down and stretching when we jump. That is completely lost. Here's an extremely old example where I tried something similar. It's sort of like an autoencoder, and I'm trying to have the character move exactly on this curve. The autoencoder itself basically just stitches little fragments together, and you can see that he's sort of like sometimes off and sometimes on the curve. When he's off the curve, that's the result of the autoencoder, and I can then optimize it and force the character to stay exactly on that path, but we get extremely weird strides. So I'm stretching the animations past what looks good. And that's the same thing that happens when I basically blend between locomotion and jumping. It's the same thing as if I have two states in an animation graph and I basically blend between the two. That will never look good. So that's basically a summary of my findings of me looking at all these research projects. And I think I could probably have lived with some of them, but what really made me look away from autoregressive methods in the first place was extraordinary long training times. In game production, when an animator gives us a new animation, or my animation director tells me, hey, this needs to look different, that change needs to happen now. We can't wait 6+ hours to train a neural network and then hope that the change that I made actually appears. And if it doesn't appear, what do I have to change? First of all, I have to wait another 6+ hours. And I can't even ask the network, why did you produce this pose? It's very opaque. So what is it that we really want in games? What is it that we want from an animation system? So I'm not sure if everybody is playing games every day, but so this is an example from Bloodborne. That's one of my favorite games. The actual locomotion is very fast. It's not a really high quality visual result, but in this particular case, it is a requirement because there are enemies that attack me. I need to, on the spot, turn around and evade. I don't care that there is no nice plant and turn. It's just not required for this kind of game. So this is Dark Souls 3, and that's just an example of attacks. So the attacks are always exactly the same length. And if you pay close attention, the attacks even take exactly the same, have the exact same duration, regardless if I'm standing or running. And that is very important because that's by design. It's an intentional choice that the animation system has to guarantee. So there are weird monsters and they attack me, and I learn to see, oh, there is an opening. And I developed as a player this muscle memory that tells me, how long does my attack take? Is this opening long enough so I can get my sword strike in? So this is an important decision from a gameplay perspective. So this is from God of War. This is a so-called second-person character controller. And here, if I would angle the camera down, the legs would actually sort of like, as soon as I change direction, the legs actually completely ignore velocity and move immediately into the other direction. But that's by design. Here, the idea is that the character takes up the same real estate on the screen. It's sort of like a shooter. I basically move the camera, and the character is just there to sort of like support the visuals. So that the guys that made the game made this decision deliberately. It's not they made bad animations. And just to state the obvious, that's from Shadow of the Tomb Raider. An animation system needs to be able to perform these kinds of movements. Otherwise, we will never use this in a game production. However fancy the motion synthesis system under the hood is, if we can't support these kinds of movements, we would never use this in a game production. So I thought long and hard about what would be the holy grail, what would be an ideal system that does not use animation graphs, what are the requirements. So first and foremost, it needs to have fast turnaround times. I think 5 minutes waiting for an animation to put in, that's fine, but waiting 6+ hours is not fine. And of course, at some point, there's a gray area. It needs to provide ground truth motion synthesis. If I put in gigabytes of data, well, somebody decided to put in gigabytes of data. We don't want to, I mean, I can make tools that tell me, hey, this is redundant, and you can snip that out. You don't need all of this, but that a built-in characteristic that basically merges similar motions, that's definitely a no-go. And obviously, minimal memory footprint. It needs to be fast and need to be changed. I need to be able to change the style of my character. That's all pretty obvious. It needs to be scalable. If I add animations, the system, by me adding a large number of animations, the system is not allowed to run much slower, obviously. It needs to be controllable. If gameplay tells me the character needs to instantaneously move to the left, well, then that's animations. That's what the animation system needs to do. And it needs to be as versatile as animation graphs. If gameplay requires that the character is climbing, well, sure. And it needs to be precise. It can't veer off from whatever the game dictates. So, and all of these thoughts went into Kinematica. So how does it actually work? So this was the prototype I started with all my weird hacks and little things that went in there. and all my knowledge that I gathered by looking at all these other research projects and my little to-do list with what would be a good system at the end. So I stuck with motion matching because I think it has a lot of good things. So I tried to solve all of them. So the first thing was I didn't want to have people write cost functions. So the solution that I came up with is, so let's say this is my reference pose, the guy in the middle, and I'm moving a little slider back and forth. And we can see that, so here I'm moving the slider to the right, and I can see another pose emerging from that reference pose going backwards. And we can see on that trajectory a little transform sliding along this trajectory. So given a reference pose, I take the entire future trajectory and all the poses that led into this reference pose and put that in a giant matrix. So the top row is the root transform that starts at this reference transform in character space. So we imagine the characters at the origin, and from there on, my trajectory emerges. And all the poses that lead into this pose are put into all subsequent rows. And the similarity function that I'm using to, so first of all, I call these matrices fragments. And the similarity function that is used to compare two fragments is a simple L2 norm. It's extremely expensive. That's even way more expensive than it was before, but it produces really good results. So if I run a very brute force search across my motion database and search for the best fragment that I can find, it works even without me writing any specific code. Given a reference pose, construct a fragment according to this, and it works really well. And I can scale the individual elements that go into these matrices to sort of like put more emphasis on trajectory or put more emphasis on poses. So yeah, the problem with this is, of course, that these fragments are extremely heavy, extremely expensive, and usually they contain more than 300 scalar values, which is then 1200 bytes per fragment. If I would explicitly store all of this, that would result for that motion database that I used in that demo that I showed at the very beginning, that alone would take up 82 megabyte. So that's not possible. So I'm using a product quantization scheme. Here's a reference to the paper if you want to look that up. So that's the vanilla product quantization idea. The basic idea is we take a high dimensional feature vector, slice that into a number of smaller feature vectors. We use K-means algorithm to find the centroid that corresponds to the individual slices. And we only store an index for each and every part of that feature vector, which what is the closest centroid that corresponds to this. All the details are in that paper, and I think it's a genius idea. And I'm using a neural network on top of that that optimizes these centroids. This is inherently an approximate nearest neighbor search, and we're only interested in a single neighbor. So that has some implications for how we can optimize this. So I think, so this is where I'm actually using my neural network, and I think it's I personally think it's a much better application of neural networks. It's very specific. It's not as elegant as autoregressive methods, but it works really well. At the end of the day, I get my fragment I hat, that is usually 64 bytes long, and that I can store in memory. And that does not take up, that takes a tiny fraction compared to the actual amount of memory that I would store for the actual animations. And then we use Unity's high performance C# to perform a nearest neighbor search. I'm using, on top of that is a hash table solution that, that brings this down to a sublinear nearest neighbor search. all of this usually executes with this amount of data, which I think is already pretty extreme, in 5/100th of a millisecond in C#. And the training time is also not too bad. I haven't gotten around to write a paper about this, and if I would want to really unpack this one slide, I would talk another hour, but I think I don't have time for that. So that's sort of like the extreme high-level overview. But there is still this back in time problem. Even if I get a, even if I find a good candidate fragment, I can still sort of like work my way back in time like I initially described. So how about that? So the solution that I came up for that is, so I just recorded this little locomotion fragment that I showed, or this piece of locomotion. So I can scrub back in time. That's what I just, that's the actions that I just performed. So now I enable the control signal. That's what I want the character to do. And now I show the candidate that was found. So every frame I perform this nearest neighbor search that I just described, and that's this yellow trajectory. Sometimes it matches, sometimes it doesn't, but it doesn't matter because I introduce what I call an anchor. That's a fragment that was found at some point, and I decided to switch to this fragment, and I commit to this until I find a new candidate in the future that is better than the anchor that I found sometime in the past. So let's say at some point, because for whatever reason, I decide, okay, this is the fragment that I actually commit to. That's my anchor. And you can see that the character is sort of like on rails on this magenta line, on this magenta trajectory until it reaches the end. And then I'm forced to make a new evaluation. But during this entire segment, I only switch if I find a new fragment that is better than that. And that completely solved this back in time problem. And it works really stable. Even if I have animations that I've only stand still, or walking animations, even if I sort of like push my gamepad just a tiny, tiny bit, it's still stable, which was sort of like one of the weirdest problems to solve, or hardest problems to solve without this idea. So, but given all of this, how do we turn this into a system that is as versatile as animation graphs? Well, this is a slide from the very beginning where I said, well, we have on one hand side the game logic, and on the other hand, we have our animation logic. So the whole idea is to completely remove animation graphs and only have that game logic. The game logic itself, I have to write in any case. There is no way around it, but of course it gives me the freedom to do whatever I want. So, but now I put a tiny little logic. So these, those dots are too dark. So these little dots inside the individual game logic states, they indicate a tiny little piece of code that performs these similarity searches. And I made these similarity searches as open and flexible as possible, so I could write whatever I want. I can search for, I'm not sort of like restricted to only search for matching fragments that match the current pose in my trajectory. That would only be usable for locomotion. That's sort of like the trivial case. So let's look at this a little bit more in detail. How does this work? So the demo that I showed at the beginning, where the character is performing ledge climbing and free climbing and locomotion, parkour tricks, at some point I had to decide, how do I want to write my game logic? So this is a very popular way of writing player control logic in games. It's basically a prioritized list of abilities. So at the and every frame I execute these abilities from top to bottom. If any of those abilities decides that it wants to take over control of the character, this is where the execution stops. So the character, I ask, hey, do you want to climb? If it says no, then I ask, hey, do you want to perform a parkour trick? And it says yes. And okay, this is where it stops. If not, I fall back to locomotion. And that is actually a pretty, it's a very common thing to do in games. And I want to emphasize, this is nothing Kinematica is sort of like superimposed on top of Kinematica. This is, you can, as a game developer, decide how you want to do this. That was just my take on it. And then these little So yeah, okay, the climbing ability that I sort of like, I could have broken this into multiple abilities because I wanted to have ledge climbing and free climbing, but I decided, well, let's see how the code looks like if I mash it all into one ability. So I ended up with this little state machine here. And again, that is logical states. I have to do this anyway. I need to sort of like at some point decide, hey, the user is pressing a button and there is a wall ahead of me. Am I close enough to allow the character to sort of like climb on that wall or not? This is this kind of code that would go in there. And all these purple dots, they are the similarity searches that run alongside my game logic to then find the necessary animation fragments. So policies, I named it policies. Maybe that name changes. I'm not sure if it's the right name, it's the right term. And I can write policies any way I see fit. I have sort of like very low-level similarity searches and some more common cases, and people can decide which one they want and write custom ones. But the basic idea is that, so for locomotion, I have one fragment. I want to find one candidate. That's a one-to-one similarity search. Parkour is a very complicated example. I show how that works in a second. There can be multiple entry points, multiple source fragments, and multiple target fragments that I potentially want to get out of this. So I can perform M-to-N, N-to-M similarity searches. Okay. So there's another piece of the puzzle that I just wanted to briefly talk about. So the actual motion library is extremely simple. It's basically a giant matrix where the top row contains the root transform across the entire motion library. So the number of columns might be like 70,000. The number of rows indicates, well, the number of rows correspond to the size of my animation skeleton. The top row is the root transform, and all subsequent rows contain the local space transforms for every joint. At least conceptually, that's how we can think about it. And given a particular row, I can always, given this idea, I can always know where would my character be in 1 second, but just looking a couple of columns to the right. So all of this can be thought of as put in this red box here, and then I use a tagging scheme that separates animations into different islands. So I can say, well, all these animations belong to locomotion, all these animations belong to parkour, and so on and so forth. And when I perform a similarity search, I can say, well, I only want candidates that belong to a certain category. And on top of all of that, I can have tagged poses. So individual poses can be associated with arbitrary data. So here's an example of how this arbitrary data looks like. I can have an entire struct where, for example, I have a transform that indicates the surface normal of a contact that my character performs at this particular frame. And all of this goes into my similarity search, or can go into my similarity search. I have an example of that in a second. So let's very briefly look at locomotion. It's the trivial case, basically. So in order to generate a control signal, a trajectory, I have my character root transform. The tail is basically as my past trajectory. That's all the transforms my character went through in the past. And the future is what I want my character, how I want my character to move. So with that idea, I can write this little toy example where given a root transform and a velocity, a current velocity, and a desired velocity, I can construct a curve. And that is basically that future part here is basically what I take, and I generate a fragment given the current pose. So the fragment contains all the past poses starting at this reference pose. Then I take this future trajectory and stick it into that fragment that indicates the future trajectory. And then I perform a one-to-one similarity search with that without any constraints, and that's it. So that's a nice side effect using this kind of scheme. I can perform collision detection with that. So here's an example where I have my character basically running against that wall, and he comes to a gentle rest. He's not running into the wall and keep running like in some games. So how does that work? It's basically a byproduct, and I can decide to have this or not have this. But if I, let's say, scrub back, I can see how my predicted future trajectory behaves. So in that case, I decide, well, I detect this intersection. There is no point in trying to get around that wall because it's a giant wall, and I run into the middle. So I basically have no other choice other than basically stop there. And the similarity search then sees, basically he wants to stop in half a second, or as I'm getting closer to the wall, I have to stop right now. And so this comes as a nice byproduct to have the character avoid collisions if I want to. So the current systems that we use can't really do this kind of thing if we think about it. So usually we have character capsules, and all we do is we calculate a velocity per frame velocity that we set as properties on that character capsule. During the next physics tick, we would perform collision resolution, and then next frame we get the result for how that character capsule move. But if I want to do this ahead of time, that scheme doesn't work. So I ended up writing a custom character capsule. So I can move that around, and I can jump, and it can perform collision resolution, and it can jump onto things, and it can slide off. So basically everything that you would expect from a character controller. But it has a nice little trick to it. So now I'm combining both ideas. So here's my desired trajectory that I construct the way I described earlier. But you can see that it respects collisions, and it slides around objects. So how does that work? So I have my character capsule, and I basically cast that forward in time as I predict my trajectory. So I predict the, let's say, 1/30th worth of time ahead on my trajectory, perform that collision detection, and depending on that, on the collision resolution, that feeds back into the trajectory prediction. It's not really too difficult to write, but it's sort of like a nice little pattern that I started using everywhere. So the character capsule is basically, I had to write my own custom collision resolution, but other than that, it's very standard. The only other thing that it can do is I can take a snapshot, I can move it, it can perform collision resolution. I can do this multiple times, and at some point at the end, I can rewind to the state where I took a snapshot from. And that I built into my character capsule, and that's all I really need to do to perform collision detection ahead of time. So how does parkour work? So parkour was designed such that it's basically different moves, and they are one-offs. I cannot interrupt them, and they are anchored in the world. So if I perform a wall run, in this case, this particular wall run has 3 contacts with that wall, and I want the feet to make exact contact. So, and that move spans some time before where the character is actually sort of like coiling up, gaining momentum, and you can see that it already belongs to this movement, and then the actual movement until some time later. And all of this is the entire move, but where I enter and where I leave is completely undetermined at authoring time. So this yellow line is the actual trajectory that belongs to the entire move, everything that is tagged as parkour, and we have like hundreds of those. And then this is where I use the markers. That's per frame payloads that are associated with individual frames. And in this particular case, I decided that I want the actual point. So which joint makes contact with the environment, and what is the surface normal at that point? So for certain other cases, when I vault over an obstacle, the surface normal goes up. In that case, it points out of the wall, right? And this transform down here is where the predicted future trajectory would intersect with this obstacle that we perform that move on. And this is the anchor transform, which is the delta that goes from that gets us from the contact transform to this particular animation frame, which corresponds to the first time where the character makes contact with the environment. So that's how I decided to set this up. But this is all logic that a game would sort of like can decide to do it this way or can decide to do it some other way. So how does this look in action? So here I can make a little editor for this particular parkour movement system. So I can preview how this would look like if I make contact with this obstacle at this point. We can see that all the contacts are sort of like exactly at that wall, and the feet make precise contact. So now I can scrub through all the different movements that we have, all the different parkour tricks. And then in this case, I selected a vault over medium high obstacle. And then I set this contact transform to where it would be logical, where the predicted future trajectory would intersect this obstacle. And I can see here, for example, the left hand makes contact as I vault over, and I can preview it, and you can see that my annotations make sense, right? So how does the similarity search work in this case? So let's say so all of this would be part of this parkour ability. So it's all part of game logic. So here's a collision, and this would be my predicted future trajectory that was generated by the locomotion ability. Then in that case, it would intersect this collision. I can calculate the surface normal. Now, for all the movements that we have, so what I'm showing here is for one movement, but I would perform this for all the movements that belong to a certain category. So let's say this is a medium height obstacle. I would go over all the motions that are, or movements that are, that correspond to this kind of obstacle. So then given some root anchor transform that I just showed in the previous slide, I can reconstruct this entire move trajectory. And then I would have an area where the predicted future trajectory and that move trajectory overlap. And given this, I can now perform an n times m similarity search. So all of this is still game code, but at this point, I can now ask Kinematica, hey, I have this situation, find me a good transition between those two. And what I usually do is I generate a trajectory that starts at where the character is right now and ends at this point, which is where the character makes first time contact with the environment, to basically bridge my predicted trajectory and the actual approach trajectory. And while I'm on this, I basically completely ignore the trajectory displacements that come from the animation to ensure that I end exactly at that point. And this is an example where I'm saying, well, I have this kind of level of control that I need for a game. Games cheat all the time. And this is what I can do here if I decide to. So here's an example: run towards wall, perform flip. So I'm recording this. So now I can scrub back. So here I perform my flip. I can see that I exactly made contact with my left foot where it's supposed to be. And as I scrub back, this is where the decision was made. And this is where we find the next fragment. This is where this is basically one frame where I perform a similarity search. So those trajectories here on the ground, the yellow one is the move trajectory, and I just previewed the move, and this is the final approach trajectory that I generate that starts at where the character is right now, and it ends in this transform, which corresponds to the frame where the character makes contact with the environment for the first time. I will go 5 minutes over time if it's okay. So how do we go about climbing? So climbing is in terms of the logic, was sort of like the most complicated state because I tried to add ledge and free climbing into one single ability. And we have a bunch of different movements that get us from other logical states into this. So as an example, this is the character mounting onto a ledge. This is dropping off a ledge, dismounting. And we have tons and tons of those movements. If it's a single animation, there would be no trick to it, of course, right? So this is one example of this kind of movement. So this is pull up while hanging on a ledge. This is dropping down on a ledge that is below the character. And we have ledge climbing. And here you can already see I'm using basically the same trajectory prediction method that I used for locomotion. As I sort of like go around the corner, the predicted trajectory follows that line, and the character nicely follows that and climbs around. And the same thing, of course, for free climbing, where the movement is basically constrained to this plane. So yes, I need to somehow decide where can my character move while he's on a ledge. So basically what I'm doing is, as I detect this collision with this object, I extract what I call a ledge geometry. That's basically those 4 lines here, those 4 connected lines. And then I can construct what I call a ledge anchor. So I can take a wall space position and how far through a percentage along that line from left to right, subject to those normals here, am I? And I can move this ledge anchor. I can say, well, I want to perform a displacement of 10 centimeters to the left or to the right, and it would automatically sort of like lead around those corners. That's game logic that I have to write, yes. The only trick that I have to do here is that I have to do this. I have to sort of like support this, take a snapshot of my ledge anchor, move it a couple of times, and rewind. So the same thing that I did with my character capsule. And free climbing is exactly similar. So as I mount onto a wall, I extract this wall geometry in this case. And given a wall space transform, I construct a wall anchor, which is a 2D position, basically UV coordinate in this plane. And as I move it, the only thing I'm doing is constrain it at the boundary of this geometry. And I support this, take a snapshot, move, and rewind. And other than that, it is extremely similar to what locomotion is doing. So I just want to point out that for any non-trivial character navigation, I have to write this kind of logic. So even if I would be using animation graphs, I need to somehow have a notion of where's my character allowed to go, right? Even if I want my character to stop in front of a wall, I would have to perform raycasts or whatever to sort of like trigger animation. So some kind of logic I have to write in any case if I use Kinematica, some other motion synthesis system, or animation graphs. So that will never go away, but it also gives us the freedom to do whatever we want in the game, and we can cheat and get the character into place if we want to. So, for example, perform a parkour move and maybe slide the character a little bit if he's not exactly in the right spot. That's all little things that we just need to do. If I want to open a door, I'm like 10 centimeters off, and the only option I have is to slide the character, then I need to be able to do that. So that was basically the long story of prototypes that lead into what is Kinematica today. And thank you for listening. And
all right, thank you, Michael. I think we have time for a couple of quick questions. Yeah.
Thank you, Michael. It was a really good talk.
Thank you.
I have lots of questions, but try to get just one. When you were talking about the neural networks, I understand that the input is constrained by the skeletal representation of the human that you use, like the degree of freedom, etc. It's fixed.
Yes.
So is that a limitation? Because at least in research, sometimes we have like different data sets of different motion captures, and I see that like converting from one to the other is always an issue. So if like everything you presented assumes that there is a constant skeleton or high quality representation.
And now okay, no, it does. In the demo that I'm showing next time, this guy actually has a little dog. And he's walking with him. So it works on an arbitrary skeleton. So it doesn't have to be a biped. It works on quadrupeds. So if I want to have, I don't know, a tail or whatever, you can do that. That's not it's arbitrary. Yes, but the training takes 5 minutes. So yes. And you can do the same things that you could do with any other system, right? You can retarget it on the fly if you really want to. But yeah, it's of course in general preferable to have animations that all belong to the same skeleton, right? So it's not really relevant to your question, but this character has 2,000 animated joints, and the animation skeleton has, I don't know, 26, and all the 1,980, 74 joints are procedurally animated. So this Kinematica produces the 26, and then I run a bunch of animation jobs that animate the rest. So you can mix and match if you really want to. And that stage could be, before you run to that stage, you could retarget it to whatever skeleton you want if you really want to.
Another question? Yep.
Hello. Thank you very much for the talk. So I noticed that in the sample you're showing, there are no slanted surfaces when doing parkour moves. Everything is either vertical or horizontal.
Come in next time I show this.
Oh, okay, okay. I was wondering if like the motion capture was difficult to adapt to slanted surfaces. Like, can you?
Yes, they only had a tiny little slope like this size, and I had to. I show it next time.
Okay.
It's, I have the most of this motion capture library is unfortunately on flat surfaces. So I do have some slopes, but I didn't have enough time to put that in here.
Okay. But the approach is going to be to capture like motion capture on the slanted surface as opposed to adapt like the vertical.
Exactly. Basically, your predicted future trajectory would just go up a ramp. And in general, that idea is not very different from what Daniel Holden and his phase function neural network is using, which he sort of like, he took that idea from Simon Clavé and me from before. So all of these papers seem to be using the same basic idea. And if you want to go up, he had, for example, this balance beam example. I don't know if you're really familiar with this paper. Basically, it's sort of like this balance beam where he restricts his future trajectory to sort of like just sort of like be on this tiny little beam that goes across a gap. And as you enter that beam, we basically request a different set of animations. So you can do all sort of these kinds of things with this idea.
Thank you.
Sure.